Today's lesson is about electron orbitals. It's a cute little cartoon there if you want to take the time to read it. I've attached this PowerPoint in Echo for you to go along with me if you so desire, or just go back to it as you need to go back to it. But let's talk about where those electrons are. So far we've talked a little bit about how we know what we know, but now we're going to actually find out where are those electrons around the nucleus of the atom. And why really do we care? I mean, why is it that important for us to know that information? Well, let me answer that second question first. It's important for us to know that information because we know what we know about electrons and how they undergo bonding. That's why we need to know where the electrons are. So that helps us to understand how atoms actually do their bonding that they're going to do. The most important electrons are the ones that are on the outside, and they're called the valence electrons. And we'll go into a lot more discussion as the year goes on about valence electrons. And to be honest with you, those are going to be the ones that we really care about. But we have to know about the inside electrons first in order to figure out how many valence electrons something has. So let's do a little background information, and let's go back and talk a little bit about Niels Bohr. We've been looking at Bohr models of the atom for a while now, and if you think about what he pictured, how he pictured electrons, he pictured them orbiting the nucleus, just like very much like planets orbiting the sun. But he was not correct. They're really more like bees around a hive. They're buzzing around and moving in a wave-like pattern. The quantum mechanical model of the atom are mathematical laws that can help us identify regions outside of the nucleus where electrons are most likely to be found. Now, if you want to get into some quantum physics, that would be something that you would take in college, but these are really beyond the scope of our course. We will go into a little bitty tiny tidbit of quantum mechanics just to understand where those electrons are located. The Heisenberg uncertainty principle, Werner, he was German and his W's are V, so Werner Heisenberg said that you cannot know simultaneously both the position and the momentum of an electron. So it was an uncertainty principle. Basically, you can find out where the electron is, but you don't know where it's going at the same time. Or you could look at it this way. You can find out where the electron is going, but not where it is. That's for really small objects, like things like the electrons. Now, so far, we've hopefully gathered that electrons are located around the nucleus in atoms in energy levels or shells. Okay, and so we see that this particular diagram has n equals 1, 2, 3, and 4. Notice as you move away from the nucleus, the number of energy levels gets larger. The symbol for the energy level is a lowercase n, and that n is known as the principal quantum number. Principal quantum number. So if you're taking notes now, this would be something that I would definitely write down. Make sure that you write down the principal quantum number, and that stands for, or the symbol for that is an N. Okay, and principal quantum number. What you would say, or how you use N, is the number of electrons that can fit into any shell, and each one of these principal quantum numbers would be called energy shells. And so you can use this little calculation that you've got right here, and it would be 2n squared. So if you had energy level 1, then you would say 1 or 2, I'm sorry, let me try this again. You would say 2 times the number, which would be 1. Sorry, it's hard to draw with my mouse. And then squared, so it's supposed to be a 1 in parentheses. So 1 squared is 1, and 2 times 1 would equal to 2. That's how many electrons that energy level 1 could hold. What if you had energy level 2? So again, using the same little formula, the n being 2 this time, plugging that in, and then square it, the number of electrons that energy level 2 could hold would be 2 squared is 4, 4 times 2 is 8. So you could figure out how many electrons are in each energy level just simply by using this little equation that you've got here. All right. Let's see. It may take me just a second to get back to my mouse. There we go. And I want to erase that. Or should I say clear? There we go. Okay, so let's talk about orbitals. This is something that you need to know. Orbitals are a region of space within an energy level where there is probability of finding an electron. An orbital is a region within an energy level where there is a probability of finding an electron. Orbital shapes are defined as the surface that contains 90% of the total electron probability. 90% of the total electron probability. The s orbital is the first shape that we're going to encounter here, and the s orbital is a sphere. If you want to just simply write S and then draw the shape, S orbital looks like a ball. Not a football, but a basketball. You could also call it a sun or a sphere. P orbitals have kind of a different shape. They look like really two balloons that are tied end to end. There are 3 p orbitals per energy level. Now, if I didn't say how many orbitals there were on the s orbital, there's only one orbital that's an s orbital per energy level. Draw one of the p orbitals and make sure that you put that there are 3 of these in your notes. And draw one of those. You can just kind of sketch it out. Looks like this. Looks like an infinity sign, or you could say a figure 8 if you wanted to. You don't have to put the axis, just get you a p orbital drawn in your notes. D orbitals have a shape. 4 of them actually look the same. One of them looks a little different. So there are 5 d orbitals. So if you want to draw one of them, you may they have lobes that look like this. And to me, they kind of look, you can say that they look like a daisy if you want to. Help you remember that that's a d orbital. And then you've got one that looks this way, so do the best you can with that. But with the d orbitals, make sure that you put in your notes that there are 5 d orbitals. 4 of them look this way, and one of them looks kind of like a donut with 2 donut holes trying to go into it. It's not necessarily really important that you know every single shape. You do need to know how many d orbitals there are per energy level. You need to know how many p orbitals, how many s orbitals. And then the last orbital that you need to know is the f orbital. Sorry, that just says a dumbbell with a donut. Very nice. Okay, the f orbital, there are 7 of these. And if you notice, there are 4 of them that look this way. To me, they look kind of like a funny looking flower. So a lot of times the way I draw them is I draw them that they really kind of look like a flower. So you've got 8 lobes on a f orbital. There we go. There's one more. Okay. So 4 of them look like this, and 3 of them look this way. Okay, sort of like kind of like that. And you got a little circle here, and then it's kind of got a hole in the middle there if you want to do that. And then you've got another circle, another little, looks almost like a donut. And your drawings don't have to be perfect. Just get an idea of what each one looks like. Make sure that you put for your f orbitals that you have a total of 7. So 4 that look like a flower and 3 that look kind of like a pacifier to me. Okay, those are called subshells. Okay, the energy level is called a shell a lot of times, and the orbital shape is often called a subshell. Okay, so let's look at energy levels, orbitals, and electrons. This chart will be very handy for you to jot down. So if you need to pause me so you can jot this down, I would do so. If you look at what you've got energy level N, So energy levels go from 1, 2, 3, 4. They could go to infinity if you had that many electrons to fill around the nucleus. Obviously, we're not going to go that high because we only have 119 elements. And so you can have as many as you can have electrons to fill. So the first type of orbital type in energy level 1 is going to be an s orbital, okay, or s subshell. In the second energy level, which is the second ring out, you're going to have an s orbital, and you will have 3 p orbitals. And we'll come to that in the chart. So for now, I'll just say it and I won't write it on there. In the third energy level, you will have an s, 3 p's, and 5 d's. And then in the fourth energy level, we add one more subshell. We have an S, 3 P's, 5 D's, and 7 F's. Kind of see a pattern here, 1, 3, 5, 7. Okay, let's go over here and let's fill out our number of orbital columns. So we have 1 S orbital in each energy level. So in the second energy level, we've got 1 S and 3 P's. In the third energy level, we have 1 S, 3 P's, and 5 D's. And then in the fourth energy level, we have 1 S, 3 P's, 5 D's, and 7 F's. And that's as high as the orbital types go in this class. There are some other orbital shapes that if you go into physics and quantum mechanics, then you'll probably learn about. I've heard of them. I've never actually seen the shapes for them. But they are mathematical probability areas where you might find an electron. How many electrons can fit into these orbitals? In the s orbital, first of all, you need to understand that only 2 electrons can fit into each orbital. So if you do some multiplication here, you can figure out how many electrons are going to be in each orbital. In the s orbital, there's only 1 of them, so you only get 2 electrons. Okay, in the next energy level 2, we have 1 s orbital, which would house 2. And the 3 p orbitals, 3 times 2, would give you a total of 6 electrons that can fit into all 3 p orbitals. Okay. In the third energy level, we've got 1 s, 3 p's, and 5 d's, so you should have 2, 6, and 10 for the number of electrons that can fit into all of those orbitals. And then last but not least, see if you can take a guess here. Good job. 2, 6, 10, and 14. Okay, so that leads us to how many electrons would you have in each energy level? And this is just tallying up, adding these up. So in the first energy level, we only have 2 electrons. And I think in the video on Friday, you saw Mr. Anderson refer to that. Then in each energy level, in the first energy level, you have 2. The second energy level, you have 8. The third energy level, you have 18. And then you have 32. Okay? Now let's take this and we're going to start writing some electron configurations in just a few minutes. But there is something that you need to see about the periodic table. It doesn't just get its odd shape because chemists thought it would be fun to make it into a castle-looking shape. It actually gets its shape due to the way that electrons fill up according to atomic number. And notice we've got blocks on the periodic table. So this first part that you see is what we would call the S block. I'm going to circle it there for you. And this would be something that we need to put on our periodic table that we colored the other day. That portion of your periodic table needs to be labeled an S block. And so it can just go over groups 1A and 2A. Notice this block, the next block I'm going to put up here, and I'm going to change my pen color so I can actually see that. This block on the periodic table is called the D block, and it's kind of the flat part of the castle. It's not the 2 towers. Okay, so this is the D block of the periodic table. Notice that we'll talk a little bit more about this, but if you don't have your periods numbered on your periodic table, you definitely need to do some numbering with those. But I would label this as the D block, and if you can make one of those cute little things like that, like this, do that, whatever you need to do just to label that as the D block. Over here in this corner, the other tower of our castle, with the exception of that one, this is the P block, okay? And then down at the bottom, these 2 that get taken out of the periodic table, this is the F block. And so those blocks need to be labeled on your periodic table. Okay, pause the video if you need to, and go ahead and label those on your periodic table that you got on Friday. The last quantum number that we need to talk about is called the spin quantum number. So the spin quantum number, I don't know if you guys can see this. I gotta move this out of the way. The spin quantum number describes the behavior or the direction of the spin of an electron within a magnetic field. There are only two spin quantum numbers, so the possibilities for electron spin are positive 1/2 and negative 1/2. Okay, take some time and write that down. There are some rules or guidelines that tell us how to write electron configurations. And one of the people that gave us some guidelines was Wolfgang Pauli. Pauli has something called the Pauli exclusion principle. And I've already alluded to this. He said that two electrons occupying the same orbital, I did say that two electrons would be occupying an orbital, but he said that two electrons occupying the same orbital must have opposite spins. Okay? All right, if you look at this portion of the periodic table, you can see the electron configurations on here. So let's kind of break this down just a little bit. Here we have hydrogen. It's in period 1, and it's in the S block of the periodic table. And notice if you're counting elements from left to right, notice it says 1, which would be this number. It's the S block, so S, and then you're in the first column on the periodic table. So everything in the first column gets a 1 beside it. Notice that correlates with what column you're in, okay? Over here, helium technically, even though it is a noble gas, really some periodic tables put it right here, right beside hydrogen, and it is actually in the S block, okay? If you want to pencil yours in, feel free to do that if you want to on your periodic table. Notice its electron configuration is again 1. There's the 1. It's an S. Whoops, I wrote over that. It looks like a dollar sign. 1. Let me try that again. Let me see if I can erase that. I don't know if I can. I don't think I can. I can't erase it. Okay, well, anyway, maybe we get the idea here. 1S, and then the electron total, you're 2 over into the block. So 1, 2, and then you put a 2 right here. Okay, we're finished with the first energy level. The electron, or the periodic table rather, is ordered according to energy levels. So look at period number 2. Period number 2, the electron configuration is 2s in the S block. Uh-oh, let me go back. Went forward and didn't mean to. So it's 2s, and you're 1 over into the S block, and so 2s1. BE is 2, here's your 2 over here in the S block, and then you're 1, 2 over, so 2s2. Now, skipping all these in the D block right now, remember this is the D block right here, we move over to the P block. Okay, because actually that's the next element in numerical order. That's number 5, boron. So we're still in energy level 2, and notice that now we say 2p. This is the first column in the P block, so we get a 1. Carbon gets 2p2, nitrogen 2p3, oxygen 2p4, and fluorine 2p5, and neon 2p6. That's supposed to be a 6. It looks like it. Okay. So the periodic table, I don't know how many times I can say this without sounding really redundant, but the periodic table is ordered according to electron filling, and it has the shape that it has because of the way electrons fill up the energy levels. Okay? So now that we see that, we have something called the configuration notation, and then we have orbital notation, which we're going to learn how to write. We have noble gas notation, okay? Always teach the long way first, and then I'll let you do some shortening up. So the first one we're going to do is we're going to do lithium, and the lithium has this electron configuration. If you take the number of electrons at the top, okay, let me show you what I'm talking about. Lithium has 2 electrons in the first energy level in an S-shaped orbital. It has 1 electron in the second energy level, also in an S-shaped orbital. Now, what orbital notation does for you is it causes you to actually show the electrons. So I'm going to fast forward this, and so we have 1, 2 electrons, and then 1 electron in the second energy level in an S orbital. The reason that you're given arrows as symbols is, remember that electron spin? That symbolizes that you have one that's spinning one direction and another one that's spinning the opposite direction in the same orbital. Okay? Let's look at beryllium. Beryllium should have 2 arrows in the first energy level, 2 arrows in the second energy level, because that's all it's got. It only has 4 electrons, so we're finished with beryllium. Boron has 5 electrons, so you start with the first energy level, second energy level, and then the 5th electron goes still in the second energy level, but it goes out into a P-shaped orbital, because remember we had S and P's on your chart. In the first energy level, there was just an S. In the second energy level, there were S's and P's. And we said that there were 3 p orbitals, and that's why you see 3 lines there for the p orbitals. Carbon, up, down, up, down, up. Uh-oh, you would expect to see it go up, down. But what happens when you have orbitals that are of the same energy? This is actually another ruling principle for drawing electron configurations. These p orbitals, these are all p orbitals, with the funky shape of, remember the shape, that funky shape, or if you drew it this way, it's like that. Okay, so what happens, these p orbitals have the same energy. Okay, and what I mean by that is they're all at exactly the same energy. It doesn't matter which one these electrons get to sit in, and they are negative, so they don't want to be in the same energy orbital if they don't have to be. And so they're going to get their own stall until there's no more room. So let's see what happens with nitrogen here. Nitrogen, we have up, down, up, down, up, up, up. Okay, so they all got their same room. And then oxygen comes into play. Up, down, up, down, up, up, up. And then we have to come back in, and somebody has to share a room. So because you can't go to the next energy level until you've completely filled the lower energy levels. So we wouldn't jump out to a 3 yet. We're still on energy level 2. All right, so we're going to completely fill up this energy level. Here we have energy level 4. Sorry, we have fluorine. And then last we have neon. Up, down, up, down, up, 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 down, down, down. Okay, so that's the first 10 electrons. And you see the electron configuration. Hopefully you notice a pattern. There's definitely a pattern there. And we've got the 3 types of configuration that we'll be knowing how to write by the end of this week. You hopefully will have this down by heart. And I'll show you how to use the periodic table, because if you don't have to memorize this, you just use the periodic table. It's already in order, so why not use what you're always going to have on the test? All right, that is the end of today's lesson on electron orbitals. I hope you took good notes over that, and you've got a practice sheet. See how well you do on that practice sheet, and I'll see you tomorrow.